hybrid functions do cause problems for some students. So the purpose of this video is just to walk you through this hybrid functions worksheet. It was supposed to be a little bit tricky, so if you found it tricky, that's good. What I'll do each question, just try to talk you through the approach I'll take. Yeah, if you've got any sort of follow-up questions on that, ask in class. So I'll just show you quickly how to do hybrid functions on the calculator, because it does do them reasonably well. So we're going to use our shift key for define f of x equals. Then we're going to go to, we're going to go back into main. We're going to go to the soft keyboard and math 3, and this is the hybrid functions template. So we want that. Noting that if you've got 3 functions like question C, you just click it again and it will add another row. So our first function is x plus 3, where x is less than 1, and 4 take 2x, where x is greater than or equal to 1. Okay, now we'll go into graph and table, and we've got f of x here, and all we're going to do is graph it, and it knows what f of x is. F of x will be that hybrid function. You could copy the whole thing over or just go graph f of x for me, please. And there it is. So that's what our hybrid function is going to look like, or that will be our target. So here goes. Alright, so let's just draw up our Cartesian plane, our y-axis and our x-axis. Okay, now what I'll do is I'll start with this one here. So x plus 3, where x is less than 1. So what I'm going to do is sub x equal 1 in to find out what the endpoint for this function is here. So when x is equal to 1, f of x is equal to 4. So that's my point, 1 and 4. And because it's non-inclusive or exclusive of 1, what I'll do is just put an open circle there. Right, now I'm noting that the coefficient of x is 1. This is just a linear function here, so it's going to have a positive gradient, so it's going to come in like this. So its x-intercept will be when f of x equals 0. 0 take away 3 will be negative 3. So there's 1, negative 1, negative 2, negative 3. Let's pop it down there. So our line is going to go like that through there and to that point there. So let's do it. Alright, so you can see that that is that one on my calculator. Right, so the next one's going to go like this. Let's just see how it pans out. So what I'll do is I'll pop 1, which is the start point of this function, into here. And we can see we're going to get 4 take away 2 times 1. So that's 4 take away 2, which is 2. So here's 4, 2 will be there, and it's including that point there. And we've got a negative gradient, so it's going to go down this way. And our x-intercept when f of x equals 0, so we're going to take 4 and divide by negative 2, so x is going to be 2. Okay, so it's going to go through there, get my straight line tool, and run it through. Right, and there's our first graph there. So we'll just note that the domain and range, so x is an element, basically because I can shove any number in this according to these restrictions here, x is an element of all reals. Y, the range, the possible y values that can come out of this. Well, if you look at it, what you can get is y values. So starting down, we're going to get negative infinity all the way up to, so here, and then we start switching over to there, we can get all the way up to 4, not including the 4. Right, so there's our first graph. Alright, so to kind of give me the space to do it, what I'll do is I'll just clear this out now. Okay, let's go on to the next one. So what I'm noting here, before I get started, I've got a basic cubic, so they look like that, and a linear function that is always 2, and that's that. So it's going to be a combination of those two things. So it's important to just look at your functions and know kind of what to expect, rather than sort of try to shove values in wondering what's going to happen. All of these will be functions that you'll be relatively familiar with. Okay, so it's going to be this basic cubic when x is less than 1. So again, let's shove 1 into it, and we're going to get 1 out of it because 1 cubed is just 1. So what will happen is the graph would go like this, will come down here, swing through the inflection point and come back up again. Okay, so let's do that. So it's going to inflect there, come up and stop there, and it's exclusive of that point. So we're going to open circle 1, 1. Okay, and then it's going to be y equals 2 from x greater than or equal to 1 onwards. So when I pop 1 into that, it's going to be 2. So here is 2, close circle, and all the values of x from here onwards produce a y value of 2. Okay, so there's our graph there. All right, now domain. X is an element of, again, you can see here that there's nowhere in the function that I can't bang in a value, so x is an element of all real numbers. All right, when is it going to give me y values? So we're going to say that y is an element, negative infinity, all the way up to 1, exclusive, union with, then we're going to get 2 out of it. So we're going to go 2, comma, 2. Actually, that should be a square brackets. This is another way of saying the interval is between 2 and 2, including 2. It's a really, really clumsy way of using the notation, but it just ensures that we only use interval notation here. What's another way we can say this? Y is an element between, so negative infinity to 1 union with the set 2. We'll put 2 into the set. Now this in some schools of thought is a combination of interval and set, but I'm pretty sure VCAR would accept that. I think that they are happy if you can define the range, so that will be fine for this question. Right, okay, let's go to the third problem. So I'll clear this out. Okay, so what do we got here? That is a truncus dilated by a factor of 2 from the x-axis, so that'll just look like the basic truncus. This one here is the basic parabola. This one here is the basic hyperbola. All right, so let's get sketching. Okay, let's start with the truncus. Okay, so what it says is it's only true from x greater than 1. So if we put 1 into the truncus, we're going to get 1 squared is 1, 2 over 1 is 2. So we're going to open circle that. Now we're going to note that what's going to happen is that the truncus basically is going to be shaved from here onwards. So it's going to go down here and approach the line y equals 0. So we better mark that in as an asymptote. So I'll just get my kind of line tool and go over the top there. Right, I know you can't see that, but on your piece of paper it does need to be dotted along that line y equals 0, and I'll look for your dots. Okay, so make sure you just dot it. Even though you can't see mine, I'll be able to see your pencil marks. Right, x squared between negative 1 and 1. Okay, so that's just a basic y equals x squared parabola. So it's going to go through the origin, and we'll put 1 in. That's 1 squared, which is 1. And negative 1 squared, which will also be 1. Not the best effort. Okay, so there is the parabola component. Okay, and lastly we've got this hyperbola, and it's being chopped at negative 1, so that means we're only going to take this bottom part here. So let's put -1 into it. So -1 goes in and we get 1 divided by -1, which is -1. So we're going to get that, and that's open circle, and it's going to go up towards this asymptote here. That's pretty hopeless. Okay, let's try that. Yeah, that's better. Okay, so there is our hybrid function. Okay, so what's our domain? X is an element of all real numbers, except I'm going to remove -1 and 1 from the set, because you notice that -1 doesn't produce a value because both of these points here are non-inclusive or exclusive, and same over here. Alright, now what about our range? Y is an element. So you can see here the lowest number I can pump out of this thing is -1, not an inclusive. Now I can get 0, so this is infinitely close to 0. I can get 0 here. I can get all of these values. My highest value that can come out is 2, non-inclusive. Alright, so there's that one. Pretty tough one. Okay, so this one here is 2 hyperbolas. Okay, so this hyperbola here has been moved 1 unit to the right. That's that. And this one here has been moved, well, I'm not sure, -x take 2. It's been moved 2 to the right and reflected in the x-axis. That's what that negative sign does there. So that will be 2 to the right and reflected, meaning that will go to there and that will go to there. Alright, knowing that, let's just see if that helps us do our formal sketch now. Okay, so let's do this one here when x is less than 1. So we know that it's going to be asymptotic at 1, so I'm going to put that asymptote in. That's x equal 1. And our hyperbola, it's just going to be this bottom half of it here. So let's get our drawing tool. It's going to do something like this. So we are going to get a y-intercept, which occurs when x is equal to 0. 1 divided by -1, so that's going to be at -1. 0, -1. Okay, now our this one here, we're going to have an asymptote at, or now I should do the other asymptote as well. So let's pop in this one here, and that is at y equals 0. Okay, there's y x equals 1. Let's put our asymptote for x equals 2. And what we're doing now is drawing this one here. So that's when it's less than 1. When it's greater than 2, means we're going to get this bottom half here. So it's going to go like this. So we're going to get something like that. Okay. Don't think I need anything else for that sketch there. No. Alright, so the last one. Okay, now x to the power of a half is equal to the square root of x. It's just the same thing. That's the second root of x. And negative x to the -2 is the same as -1 over x squared. So what we've got is a combination of the square root function and a reflected truncus. Okay, let's draw them. Okay, so the square root function starting at 0, that's going to be like that. Don't need any values here to commit to. And this one here is the truncus. It's the negative 1 on x squared, so the root function goes like that. Truncus reflected goes like that. This is for the values less than 0, so it's going to be down there. I was about to hit what will be the asymptote. Right, so let's draw in our asymptotes. So that's the line y equals 0. X equals 0, by the way. So that's x equals 0 and y equals 0. So we've got our two equations represented, or two parts there. Right. State the rule of the following piecewise defined function. Okay, so what we've got here is a linear function. It's defined for the values of x greater than 2. Here we get a parabola defined between the values, so that's going to be 0 less than or equal to x less than or equal to 2, and these are the values of x less than 0. Okay, so this line here, it's got a point 0, 0 and negative 2, negative 2. So you could punch out the gradient knowing that the y-intercept is going to be 0, or we can note that as x decreases by 2, the y values decrease by negative 2, or as x increases by 2, the y values increase by 2. This is a gradient of 1. Okay, so this is going to be the line y equals x, or f of x equals x, for the values of x less than 0. Alright, what about the parabola? Well, what we can see is that it's got a turning point at 1, 3. Okay, so TP is 1, 3. And another point on this is going to be, so this is 2, this is 1. So 0, 1 is another point. It's also the y-intercept. So what we can do is use our knowledge of turning point form. Y equals a, x take 1 all squared plus 3. So I've just put in the turning point in turning point form, and I'm just going to use 0, 1 to find out whether there's a dilation factor. I hope I put one in. 1 equals negative a. So that's going to be negative 1 squared is 1. So it's going to be positive a plus 3. A is going to equal negative 2. So there, with negative 2 going in there, that's our equation, negative 2, x take 1 all squared plus 3. Alright, and this linear function, we're going to go a coordinate on it, which is when x is 2, y is 0. When x is 4, y is 2. Alright, and what you can see here is, so as it increases by 2, it increases by 2. Again, this has got a gradient of x, or 1 rather. And the y-intercept, I've assumed plus there, it's going to be minus. So it's going to come back through here, and I think it's going to be negative 2. Right, let's just try it out. So I'm going to pop 4 into my equation. So when x is equal to 4, 4 take away 2 is 2, y should equal 2. Yeah, that's the rule. So we've got 1, 2, 3. 3 rules and the domain. Okay, consider the following function. Okay, so interesting, that's a circle, that's a linear, that's a linear. So f of 0. So what you do with 0 is you work out which slot it's going to go into, and 0 is going to go in this because this is where the values between negative 1 and 1 go into. So 0 goes in, 1 take away 0 is 1, square root of 1 is 1. 3 is going to go into this one here, which is 4. Negative 2 is going to go into this one here. Negative 2 gets negated, which becomes 2. 2 take away 1 is 1. 1. Where's 1 going to go? 1 goes into the circle, so that is going to be 1 take 1 is 0, square root of 0 is 0. Sketch its graph, ensuring that you include all key features. Okay. Okay, so this one here, -1, I'll pop in first. So -1 goes in there, and we get -1 goes in, that's -1, which is 1. 1 take 1 is 0, not included. And a negative gradient means it flicks up in this direction. Alright, so there is the start of it. Alright, now what we've got here is the circle. So this is a circle. It's the top half of a circle because that's plus. So, and its radius is going to be 1. Alright, now how do I know that? I'll just show you quickly. So I'm going to replace f of x with y and write down 1 take x squared. And I'm just going to transpose this. Y squared equals 1 take x squared plus y squared equals 1. So I've reverted to well, that's the unit circle right there. So that form there shows that it's a circle, center at 0, 0, radius of 1. Okay, so, and the plus here, when it's been transposed, means that the negative, the plus or minus, has been discarded, which means that it's the top half of a circle only. So that is going to be a circle like so. It's not the world's best circle. Okay, now let's put 1 in there. So 1 goes in, 1 plus 1 is 2. So here's 1, there's 2, 2 comes out, and we've got a positive gradient, so it's going to do something like that. Okay, so there's that, including all key features. So -1, 0, 1, 0, because those are included. Yep, I think that's all key features. 0, 1, y-intercept. Okay, the domain, x is an element, all reals. Y is an element. The smallest number is 0, inclusive, so let's square them off. And the y values, I think it's to positive infinity. Okay, because these produce to positive infinity and these produce to positive infinity. So, yeah, positive infinity. Okay, this final question. Yeah, this is a ripper question from Further Maths, actually, 2016 Exam 1. It's question 8, which means it's their toughest linear problem for the state. Okay, so what we've got is Megan walks from her house to a shop that's 800 meters away. The equation for the relationship between the distance in meters that Megan is from her house 10 minutes after leaving is this. So we can imagine this as a function f of t. They don't do functions in Further, but we can imagine this as a hybrid function f of t. If Megan reaches the shop 10 minutes after leaving her house, the value of a is. So we're looking for what that number is. Alright, so let's sketch this thing. Okay, so what happens is we've got 100t being the function from 0 to 6. So here's 6. 6 times 100 is 600. Okay, so that's what happens first. So this is the time and this is the distance. Alright, so then it stays at 600. So obviously she bumps into someone, or I don't know what it is, but she bumps into them, starts talking, okay, for that many minutes. I'm not really sure how long. Alright, but eventually she gets going again and follows this equation here, kt, between a and 10. So 10, and it's implied she reaches the shop 10 minutes after leaving her house. So the shop is 800 meters away, so there's 600. It's not really to scale, but it doesn't matter. It's just going to help us plot what roughly the graph looks like. So 10, 800. This point here is a, 600, and this point here is 6, 600, and the origin. Alright, so what I'm going to do to solve this one, so I need to work out the value of a. Now this line here, imagine this line here, this is just the equation y equals 600. Right, there it is there. Now if I get the equation of this line here, right, that line there, I can let it equal 600, or I can work out simultaneously if you want, when this line here intersects with this line here, and that's going to give me the value of a. Right, so how do I know the equation of this line here? I know that that's 10, 800, that is a 600, okay? But what I actually know, they give it away in the problem, it's just kt. This implies that the y-intercept is plus 0. So they're noting that it basically saying is that this line would continue, and I know it's not to scale, but if you wanted to imagine it, it continues and will go through the origin. So our second point on this is going to be 0, 0. Right, so we can find this equation of this line here by simply doing our gradient formula, which is y2 take y1 over x2 take x1. M is going to be 800 over 10, which is 80. So our k value here is going to be 80, or it's going to be 80t. So all we're going to do now is say that this equation here, 80t equals, so let's say, when is it the same as the equation y equals 600? And if I solve this for t, okay, what that's going to give me is the time when this line here is the same as this line here, i.e. the a value. So t equals 600 over 80, t equals 30 over 4, t equals 15 over 2, or 7.5. Pretty tough problem, that one.